Today we want to talk about DSC and especially the chip DSC, especially the chip DSC sensors. And what we do today is maybe a bit new. As you know, I'm developer and researcher, and so today I want to share with you what we do if we design a new sensor layout or an adjusted sensor layout, and have a look uh, about the related investigations of these new sensors. So just a short look out, there are new sensors for our chip DSC, and also some new recommendations what sensor you should use, you or your customers, of course. So at first, hi, I'm Michael. I'm a product specialist for DSC here at LINSEIS. I'm at LINSEIS since 2017. If you want to contact me, you can do this through LinkedIn, by mail, or by phone, of course. So it shouldn't be so hard to contact me or to get in touch with me. For all those who don't know LINSEIS, we manufacture instruments for thermal analysis and the determination of thermal physical properties. And we are a family-owned company founded in 1957. Our headquarters here is based in Selb in Germany, but you can also find us in USA, China, and all over the world. I think we're pretty innovative, and so there are many special devices adapted to the customer needs and requirements. And maybe the chip DSC and especially the new sensors are part of this adapted requirements for some customers. Let's go on. Here you can see our complete product range, and there are many devices we could offer. Simultaneous thermal analyzers, thermal balances, whatever you can see here on this screen. But today, of course, we want to talk about DSC, the Differential Scanning Calorimetry. And I think this is at marketing here. At first, I want to explain the chip DSC itself just for a minute. So as you know, the DSC, the Differential Scanning Calorimeter, is based on a sample normally and a reference. So the sample, for example, is here the blue sample, and the reference right and picture. And only with conventional DSCs you have a surrounding oven with the heater, and at the crucibles with reference and sample there are the thermocouples or whatever the temperature sensors at all. What we do with these here is we converted this design. You can see here in the mid. So now the reference and the sample aren't horizontal, they are vertical in the chip DSC design. You have the sample. Below the sample, of course, the temperature sensor for the sample. In the middle of the sensor, you can find the heater. Below this heater, the reference sensor, and below this reference sensor is a fixed reference. So that's all. So that's what we've changed here for the measurement cell. There are some advantages through this design. We are much faster. You don't need any reference crucible anymore. You don't have to place it. You don't have to fill it with inert material. But of course, there are some other things. You also have to take care about this. So the DC signal itself could be slightly or baseline itself But all of this does not affect the transitions we are looking for. So the DSC is full DSC, just with a slightly different layout. By the way, the sensor itself is made of ceramics, and all of the sensors are inside. So if you, for example, break the sensor or something happens with it, you just have to replace the sensor itself. You can do it by yourself. And yeah, in comparison with some other devices, it's pretty easy and also cheap to replace the sensor, and everyone can do this. Okay, so this is basically the chip DSC, but do you see at all what are we looking for here with this device? Here you can see a diagram from the literature. In this case, it is PET or reference material also. And here you can see some different transitions. So at the upper measurement, you can see there's a transition peak in the beginning. Then you can see that the cold crystallization, crystalline melting and oxidation, or the thermal degradation. And below this measurement, you can see the cooling. And yeah, the cooling is just the crystallization. And of course, again, the TG, so the glass transition in this case. The DSC takes care about the enthalpic transitions. And yeah, so we need any enthalpic change here to see any signal. And yeah, sometimes there are some overlapping transitions like double peaks, or for example, the glass transition with the realization peak at the beginning of the first measurement curve. And so for different transitions, sometimes we need different sensors or different conditions for the measurement cell. Some transitions, for example, the melting of metal or something like this, or double peaks with metal alloys and polymers, we need a very, very fast system, a fast measurement system to make clear what is the first peak and what is the second one. But for other transitions, for example, the glass transitions, we need the highest possible resolution. So the speed of the measurement system isn't so important here because the glass transition itself lasts some time anyway. So here we are interested in the highest sensitivity of our measurement system. Yeah, and this is the reason why we do this, why we adjust our sensors and optimize them. So yeah, what are we looking for? We are looking for specialized sensors for specific investigations, because it could be necessary. This depends, of course, on the application of the customer. And yeah, that's it. And today I want to explain you how do we do this? What is the way how we can do prototyping, and what's the actual result of this development, and what are the investigations? Yeah, so we can recommend the new system. And yeah, I already explained. Yeah, sometimes you need a faster system for fast melting peaks and double peaks. Sometimes you need the highest possible sensitivity for really slow or really small transitions. And this is the reason why we say, okay, we need a higher sensitivity here for the systems, and we don't care so much about the speed of the measurement system, so the time constant. We are interested in a maximum sensitivity here. So now let's talk about the what to do and what do we want to reach. So what we want to reach, I already explained. We want a higher sensitivity. Now we mentioned okay, we have the standard sensor here on the left in this screen. So as you can see in the mid, there's a heater. Below this heater is the reference temperature sensor, and above this heater is the sample sensor. And above this, of course, our sample. Yeah, so this is the layout. What we do now is we change the space between the heater and the sensors, the temperature sensors. Or more important, we change the distance between both of these sensors. So as you can see, the heater itself is still in the mid, but the space between reference and sample sensor is much bigger. And this leads to a higher temperature gradient because, as you know, if there's some reaction of the sample, for example, melting or something like this needs some heat because it's an enthalpic transition. This way we can see a temperature change between these two sensors, and this is what we detect. And yeah, with the magic called our calibration, we can say, okay, this is, for example, 10 joule per gram or something like this. And as you can see with the bigger layout, we have a higher temperature gradient because the heat from the heater itself or the heat between the sample and the reference sensor is much bigger. So, okay, this is the theoretics of the delta T. And this is what we say, okay, we want to reach this and we can perform this. Okay, but yeah, this is the theoretics. Now we have to check, is it possible anyway? So we should have a look on the preconditions and the, yeah, for the maybe upcoming problems we could receive here. So the space between heater and sensor, as you have already seen, is still the same. So the distance between heater and the sensors is just scaled. So the heat that comes from the heater is for sample and reference still the same. Okay, this should work. There isn't a hotter sample side or a hotter reference side in this case. Okay, everything solved. Now we should have a look on the convection here. So as you know, especially above 400 degrees Celsius, convection is pretty important for DSC, and so we should have a look if we change the size of the sensor here in the height. Are there any problems we could receive? And yeah, this way I can say no, because the shape of the sample side and the reference side in comparison to the height of the sensor, so the sides itself are much bigger, so we won't receive a problem here theoretically. But later we should have another look on this on the hands-on, so we will see it on the measurement signal if it works or not. So yeah, another thing is the temperature of the sensor. So the maximum temperature, the maximum heating rate. Does this change development? Not really, because the resistance is comparable with the old system or with the classic system. And so we can also reach the 600 degrees here or slightly above. And yeah, everything is fine so far. And pretty important for our customers and maybe you is, does this work with the existing hardware? And yes, it does. So it was already prepared for our sample holder, as you can see here in the pictures. So on the left side, there is our standard sensor. And on the right side, there's the bigger one, the new one, the new prototype in this case. And yeah, it still fits. And the electronic and the mechanical preconditions are fine. So we should work, we could work with the sensor layout. And then we go for execution. So we start producing the prototypes, and then we have to test them. And this is what I want to show you later, because we want to compare the performance of both systems, of course. So now you see another one here, a smaller one on the upper left corner here. So as you can see, there's no border for the sensor, because when we start the prototyping, we already created some different types of prototypes. Some are thinner, some are thicker. I will sum this up at the end of this presentation. There will be another webinar in October where I can tell you more about what about a thin sensors. So yeah, there are several types produced, and as I already mentioned, and as you can see here on the pictures, they are compatible. There's a good compatibility for the existing construction, and all in all, it's still the same type of sensor. So it's still a ceramic monolith, and yeah, it's just a different size. And we want to check what's the influence of this different size here. Okay. First of all, of course, we have to do a calibration. So, and we want to compare the reproducibility, and yeah, what I can say, they are comparable. The baseline, the shape of the baseline is basically the same. So all of our software correction and so on still work. Why is what's the matter for this? Convection and the heat radiation is still the same, because the shape of the sample and the reference site is still the same, and also the size of the reference below the sensor and the size of the ceramic above the sample sensor is the same. So this works perfectly here. But what we can see here is the higher offset on the red curve. So our new prototyped extended sensor layout. The reason for this is pretty simple. So we have more material, so we have to heat up more material. So the heat capacity of our new sensor is higher. And yeah, we can see this here, the offset is bigger. And also it's takes some degrees more for a perfect baseline here, so we can do the evaluation maybe some degrees later in this case. But the most important thing in this case is all of our peaks over the whole temperature range are higher. As you can see here, we will compare it for indium directly, but this is what we want to reach, and as you can see, we reached. The scale, by the way, is the same of both diagrams. So we receive a higher signal here. And maybe now you're wondering, why do we show microvolt or volt in general here in this screen? The reason is if you melt down 5 milligram of indium, maybe with a better, maybe with a not so good measurement system or a not so sensitive system, the enthalpy of 5 milligram, the melting enthalpy, is still the same. And this is why you will see a big difference between the two peaks. And this, for this reason, we use the DTA signal here, because this is the not enthalpic calibrated signal, and this is important here in this case to compare the performance of the system. So yeah, this is the reason for this. You will see in the coming slides, we will always plot the microvolt or the DTA signal here in this case. All in all, the main advantage we want to reach is approved. And so we can go on with the evaluation of our peaks. So the most common material here is indium. So of course, I also want to use indium. And now let's have a closer look about the performance. The indium height to width is a standard method to compare measurement systems. And so what we do here is we use the temperature range of our peak at 50% of the peak height, and we also use the peak maximum for the calculation. As you can see there, it's for the extended sensor layout 0.137 to 3.2 Kelvin. And this is how we calculate the indium height to width ratio. And what we can see here is that they are basically the same, almost the same. Of course, you can see there the extended sensor layout is still a bit lower than a classic sensor layout. All in all, without any measurement conditions, they are the same. Now, we're wondering what's the reason for it. As you can see here, the peak maximum of the extended sensor layout is higher or lower in this case than the classic sensor layout. But if we compare the temperature at 50% of peak height, we can see also the peak is broader. And for this reason, the indium height to width ratio for the sample, by the way, the same sample, of course, is the same here in this case. But what's also important is the signal noise ratio, the SNR. I don't evaluate it here because it's quite simple to explain, because the reference site and the sample site above the sample sensor and the reference sensor is still the same. So also, and of course, also the electronic is the same. So for this reason, also the noise is the same, but we can see our peak is around about 30% higher here in this case. And yeah, so the signal noise ratio is also better. So, okay, this is the result of signal noise ratio and indium height to width. But now, yeah, where the pros are, there are also some cons. And in this case, it's the time constant tau. So what we do here for this evaluation is we take the level at 90% and 10% of the falling ramp. So after the peak maximum of our melting peak, and then we do our evaluation. And as you can see here in the screen, the tau of our extended sensor layout is 2.86 seconds for this sample and this heating rate. And for the classic sensor layout, it's 2.32 seconds. So the classic sensor layout is around about 20% better than the new prototype. But of course, yeah, it's logical because the sensor is bigger, so we have more heat capacity, and this is the reason for the higher tau, for the higher time constant. So this is the con of our new prototype in this case. But yeah, as you know, not everything is made of metal. So for a more realistic sample, we use also a well-known sample, is our LINSEIS PET reference material. And yeah, so at first we will have a look again at the ETA signal you can see in the top of the screen or of the diagram. And there we can see there are some huge differences. So all in all, higher transitions we can see here. And what's important here in this case is the higher TG, the higher glass transition at around about 80 degrees. So this transition in the ETA signal is much higher. And yeah, so this is exactly what we want to see here. But now we use a DSC because we want to evaluate enthalpies. So now let's plot the enthalpy calibrated signal. You can see there at the bottom. And yeah, there the difference between the two measurements isn't that big, as you can see there. Yeah, and if we have a look on the glass transition there with the zoom label, with the insert view, yeah, the height of the step height of the glass transition is basically the same. And of course, this is also logical because we use almost the same sample amount here, and the material is the same. So also the measurement curve should be the same. But what you can see there is the red one. So the new prototype, the extended sensor layout, is much clearer without any noise there. And in comparison, if we zoom in that much, we can see there is some noise on the classic sensor layout. And this is what we want to see here because, for example, we use just 10% of this sample, or we use another sample with much smaller transitions. So then it would be hard to detect these transitions. And in this case, smaller noise is pretty important for a clear evaluation of our signal here, of our transition. So yeah, for a clear visibility, this is pretty important, and this is exactly what we want to see. The enthalpy of the sample, of course, is still the same, but the visibility of our transitions is much better. So maybe another sample, it was quite a hard sample, the milk powder. So we use standard milk powder. Normally it's pretty easy to measure, but we just have really small amounts of sample here. And also this, it's in powder at all. So the contact of the sample with the crucible and the sample, sample size, so the sensor at all, isn't that good. So here I've compared what about our recommendation? So we have in powder, the transition is pretty small, and also we have now different sensors. The black curves are again two runs with our classical sensor layout, and what we can see here is we can't see anything. So it's not possible to do a valid evaluation here in this case. So I've used a better matching crucible here, so our small crucible. The measurement settings are still the same, so they're identical, and I've used the extended sensor layout. So with our small crucible, we have a lid we can use there, and so yeah, the sample itself is slightly compressed inside the crucible, so there's better sample contact, and of course we have 30% more signal. And as we can see here, it's still a small transition, but it's possible to evaluate this clearly and also reproducible. And yeah, so this is why we give some recommendations and how the new sensor works. Of course, we also need the right crucible for our application. We need the right measurement conditions, but all in all, the 30% more signal are pretty important for such small transitions like glass transitions for food industries or something like this. So let's sum up. We have here a better sensitivity with our new sensor, with our extended sensor layout of around about 30%. But also, as you can see here in the direct comparison, we have 20% higher time constant. And of course, for fast transitions, we want really small time constant to evaluate double peaks or something like this. So we have a new sensor with higher sensitivity, but also the classic one is still important for fast melting peaks and fast transitions at all. So all in all, the application determines the choice of our of the matching sensor. And yeah, so it always depends on your sample and the investigation you're interested in. And now, as I already mentioned, I want to give a short overview, a short outlook of what's coming next with our chip DSC. So yeah, the development ends. And yeah, there are some ideas, there are some prototypes we could evaluate, and this is what I want to show you right now. With the schematic on the left side, you can see here. So this is the classic one. This is the well-proven sensor here for our DSC. It's yeah the best compromise between signal height and time constant. So it worked until now for almost every application, and yeah, works still pretty well. And yeah, the universal sensor, if you don't have any specific thing and you want to do almost everything with your sensor. And what about the convection? What about the noise? There's another prototype. We, all in all, we still have to test them before we can, yeah, give them to you to test for your application. But all in all, what about the bigger reference side here on the bottom? So the distance between the temperature sensors of sampler reference is still the same, so the sensitivity is still the same. But with a bigger reference, we achieve less convection. So it's just the susceptor inside the sensor. And yeah, so with this way, we can use bigger samples on the top with still a flat baseline. So if you have bigger samples, you can use them with a higher heat capacity, so the correction for the software is much easier. And as I already mentioned, we have a lower influence of convection here in this case. But there's another opportunity we have here. What about if we want to do very fast measurements, or we have a crucible we have to use, but it does not fit in our sensor. So this way we can delete this way the positioning border of our sensor, and this way you can place almost every crucible on your sensor. And also we have less LTCC level, layers, so less ceramic layers we use here, and this way we also receive a lower time constant. Next one is what we already knew. So what I've presented today is our extended sensor. So we have a higher temperature gradient here in this case, and this way we have a higher signal. But of course we have more ceramic layers, and this way we have also a bigger time constant. But what about the reverse option? If we want to have a pretty fast thin sensor with a minimum of heat capacity, of course, also this is possible. So now we have the smallest possible time constant for our chip DSC sensor this way. But of course, also we have a smaller temperature gradient, delta T, and so also the signal will be lowered. But if you have pretty fast transitions you want to detect, or you want a maximum for heating and cooling rates, of course, this could be an opportunity, this could be the solution for your application.